Welcome to Optimization for Machine Learning. So my name is Martin, and together with Nicolas Flammarion, we're gonna host you the next 13-14 weeks or so with videos on YouTube. So this course is about optimization and applications to machine learning, and we're gonna mostly focus on scalable gradient methods. So give you an introduction to the basic elements of all these methods. So for the start, we have to start with basic concept of convexity and so on, and then we will introduce gradient-based methods, which are iterative methods to optimize an objective function efficiently. We will also briefly discuss on variants of that. For example, when you have constrained optimization problems, more efficient variants, which are very relevant for machine learning, and also advanced topics which are particularly relevant for machine learning, for example, for distributed learning to have more scalability, parallel algorithms to run gradient descent. We will also touch a little bit on gradient-free methods, when you don't have gradients available at all, no derivatives. And then on the other hand, second-order methods if you already have additional gradients information, so to say, gradients of gradients, which would be methods like Newton methods, which you might have heard of it. That's the plan, and what this is going to look like from an organizational point of view is that it's very simple. So every week we will post a new video, usually on Monday, about the lectures. You will also have the lecture notes and slides, which we post on our GitHub. So we also have an exercise sheet, which also appears as a PDF on the GitHub every Monday. So it's important that you look at the exercise sheet during the week, so that then when you come Friday, when you join our exercise sessions on Zoom, that you're prepared and already can discuss the solutions. So during the week you should try the exercises yourself, and then on Friday the assistants will help you also discuss solutions or discuss how to solve it. Then you might be interested in the grading, of course. So this is a 5-credit course. You will get 20% from your project, and then we have 80% of the grade, which comes from the standard final exam, which is written, so a theoretical exam, which will be in the exam session. And all the details are always on our GitHub available. Please check it out. And there you will also find more information about the project. So this is a cool opportunity to work in a team with 3 people, to then try out practically how some of the algorithms we discuss in the course work for concrete applications. We usually encourage you to try this on some deep learning or other machine learning applications, and empirically look at some phenomenon. Can you actually see some of the things we discussed in theory in the course? Can you actually see them in practice? And what do you observe when these optimization algorithms we discuss here are applied to real deep learning problems? And you are completely free what topic you want to choose there, what problem you want to choose. We allow you to play with anything you like, as long as it is a little bit machine learning related. So you will also find several ideas in the project description on the GitHub. So there is a PDF there if you want to have a look on some ideas, but you can also bring your own ideas and study the practical performance on, for example, deep learning problems, or to do something which is like an experiment section of a deep learning paper, to see, do these experiments make sense? Are they consistent with the theory? Do we get some insights from the practical performance of this optimization algorithm? So that's for later. You don't need to worry about this in the first week yet, but have an eye open for finding 3 people to help you with that project. It's in a group of 3. Okay, I guess then we are ready to dive into the materials. And so we start to formalize this a bit, that we are on the same page with notation. It's very simple, don't worry, but we have to just make sure we are using the same kind of notation and terminology. So what we usually do is we have a mathematical optimization problem of this form that we want to minimize some objective function. It doesn't matter if you minimize or maximize, because you can just maximize minus f if you want. And we have variables which live in some, can be in one dimension, can be in several dimensions. So usually it's in a d-dimensional space. So here our variable x lives in d dimensions. So this is the setup, and your task is to find the point x which minimizes the f over this entire domain here. So this is the optimization domain of this function, so it's defined on the whole domain, and that's the task. And then the objective function, that's f, so we also call it just the objective. And we have some standard assumptions on the functions we usually optimize. It depends. We will see in different chapters which assumptions are crucial and not. For sure, we will usually have continuous f functions. And to make things simple, when we work with derivatives, we would also like these derivatives to be available. Therefore, we want f to be differentiable usually. So pretty basic so far. And why is this optimization even interesting or useful? So basically any optimization problem can be written in this form or small variants of it. But why is this useful? So optimization is used very broadly in all kinds of applications. So for us, of course, the most interest in this course will be machine learning, but most of the tools we actually learn in this course are generic, so they can also be applied to a whole other zoo of optimization tasks which come up in many applications or other sciences. It is often possible that you can formalize your problem as a mathematical optimization problem. So that's what we have here, which is called mathematical modeling usually. So what that means is you just set up, you formalize to define your objective f and a suitable constraint set and modalities to see to define the right metric, right? Your optimization objective is a metric which measures if you succeed your goal or not. It gives you a quality. So you set it up and you say that, okay, now I have formalized my real world problem. I have formalized it in a mathematical optimization problem with an objective and maybe some constraints or properties. That's mathematical modeling. And then once you have that, you take that optimization problem and you give it to for example, a solver. Standard solvers are available for many of these problems. And that solver will maybe find you the optimal solution, the minimizer, or it will find you an approximate solution. Or you can run your own algorithm. That's what we're mostly interested in this course, that we really understand how the optimization algorithms behave on such a problem. I just want to make this distinction clear that the two variants here are not the same, and we also have this almost the same distinction we also have in machine learning, where we have someone needs to define the machine learning model. Let's say we want to predict the weather tomorrow with a logistic regression. So the person has decided that the weather here is behaving like a linear logistic regression. So that's the model we do in machine learning here, is choosing the right machine learning model. And then the second task we have is to then actually solve it, which means training it, right? In machine learning, finding the parameters which minimize the cost of your model, which minimize the loss of your model. So that's the optimization. And that's the training of machine learning. So that's what these two parts mean in the machine learning world. And what of course, you can also just run standard optimizers, which are available in all deep learning libraries like PyTorch and JAX and TensorFlow and whatnot. But what we want to do here is to actually go a bit deeper and see what are really the fundamental aspects of these optimization algorithms, as they are like iterative, stepwise algorithms. How do they behave? Like, when do they perform good? When do they perform bad? Can we improve that they perform well in some cases? Can we understand what's the differences? Is this optimization method, like Adam, whatever, is it better than these other optimization methods like stochastic gradient descent? So that's the type of question we want to look at in this course, to ask a bit like why and how do these methods work, and we will try to keep a connection to machine learning, but the focus in the course is really a bit on the optimization aspect. So everything we learn here will also help you if you want to apply optimization to other problems or other applications. All right, that is just for setting the stage a bit. So of course, optimization algorithms are very well known. You've probably seen many of them already, and what has been interesting in developments in machine learning in the last 10-20 years is that the optimization algorithms almost have become simpler than they used to be in the past. So in like many years ago, like after the 50s or so, during the Cold War, people have developed very advanced optimization algorithms, for example, interior point methods and second order methods which use the gradient of the gradient, second derivative, methods which are very sophisticated but which have a computationally high cost in every step. And now in machine learning we have seen a bit an opposite trend, that we have seen that the more and more machine learning and deep learning applications have converged to use very simple algorithms, which are just first order methods, which means just use the first derivative, only the gradient, because they are computationally much more efficient and can be applied particularly well to objectives in machine learning, where we have an additional structure in the problem, that machine learning problems are always formulated as to minimize the sum over all data points, right? We have the losses of each data point, and then the overall task of training is to minimize the sum of all these losses, or the average of these losses. So that's why we have seen a huge surge of popularity of stochastic gradient and some variants, which are basically used for all deep learning applications at the moment. But still, we also want to understand the basics and the landscape of all these methods. About the history, of course, gradient descent is very old. It's from the 50s, but not the 1950s, but 1850s or so. So then 100 years later, there was a large body of work coming from like operations research to do optimal logistics and this type of continuous optimizations, which led to the development of linear programs, which are linear objectives over linear constraints. And then also convergence rates have appeared to understand how fast are these algorithms actually, gradient-based algorithms. And today, people have tried to even, there is a trend to understand the optimization algorithm together with the machine learning models, that we have to kind of study both together, that this algorithm, stochastic gradient descent, on this type of neural network together, they behave like this. Because the neural networks alone, we cannot perfectly optimize them anyway. And also we see that there's many interactions between the optimizer, which trains the network, and the network architecture. So some architectures are easy to train, but it matters where you initialize your training. So the initial point of optimization can have a big influence. And that's because these networks are so non-convex. It's not just the easy landscape as we usually have in toy problems. So that it becomes interesting to study that this algorithm together with that particular neural net model is very good for learning, and they go well together. That's just to give you a glimpse of what's the type of research that's currently happening in optimization for machine learning. But don't worry, this was just a very brief glimpse of what's happening in the history. And of course, in this course we start from the basics, so we will start with gradient descent, give you the fundamental building blocks to then see how this behaves on a large-scale machine learning problems. So this is the plan, and to give you another kind of taste how this works, this is maybe the simplest optimization algorithm in the world. This is just coordinate descent, and here we are optimizing a function which has two variables, so 2 dimensions for our x. And what we want to do is to find the minimizer of my f. We usually call that the x star. We say this is a point which is at an optimum value, so which minimizes f of x. We want to go there, and we have to start somewhere. So we start somewhere. We will just minimize our objective function on that line, which corresponds to when I just change one of the 2 variables, right? So the variable 2 here I keep fixed. The variable 1 I perfectly optimize. That's what coordinate descent does. If I choose to update the first coordinate from my starting point here, it will go up and down here and see where is the minimizer on that line, and yeah, here it is. So that's my next iteration. So you go from, so this is my point 0, I go to my point 1, and now I choose the next coordinate and I continue. So this works perfectly fine if you have many coordinates, like d of them. So now you go here, that's your x2, and then you go here again to the minimizer, and here. So this is what coordinate descent does. Okay, so that leads you to this kind of sequence, which brings you in every step a bit closer to the optimal point here. It doesn't exactly bring you there, but it gets you closer in every step. And now, of course, it's very reasonable to ask, like, how many steps do I need to get to some accuracy of how close we can get? And that's the type of theory that we are interested in, like, so how many steps to reach accuracy. And what I should have said, of course, in this example, this oval points, this kind of ellipse here indicates the level sets of the function. So if it's dark gray, means like it's further down in the objective, so it's a better objective. So these are called level sets, but we will get to that. Here we just used a very simple quadratic objective to illustrate how this algorithm behaves. You can already see, of course, it matters a bit where you start your optimization, and that is also something that we will study in this course. So that was just an example, and we will now use the fundamental building blocks from Convexity, and that will help us to then get to the convergence properties. So how does gradient descent actually converge on different types of functions? So it depends on what assumptions you have on your function. Is it a nice function or a not so nice function? So the very nicest class of functions we know are the convex functions, and there is a big, very useful and rich theory about these, also together with like convex sets and so on. So we should briefly recap the basic tools we have from there. And before we go to the functions, we also should briefly check about Cauchy-Schwarz inequality, which is just one of these nice building blocks we're talking about. And what it means is that for any 2 vectors in our space, so let's assume usually we work in d-dimensional space, and what we want to show is that whatever you do If you take an inner product between two vectors, you take its absolute value or not, you don't need to do that. If you just take the inner product, it will be smaller than the product of the two norms, the two lengths of these vectors. So that's Cauchy-Schwarz, and this is true for any u and v vectors. And how do you prove that? That's something which is very nicely described in the lecture notes, so please take this as an opportunity to check the lecture notes and get up to speed with how we can do this kind of basic proofs. And this also gives you a good feeling of the kind of geometry that we need. So, I mean, geometry is very tricky. In d-dimensions, we cannot really have much of an intuition. That's why, so that's the bad news. The good news is that there is only a very small number of tools and facts and which are even possible to use in these high dimensions. So we just use tools which are very basics. For example, this inequality here. And with that, we will be able to do most of the proofs in this course. So this, of course, is a very important inequality. And just you also know, of course, the notation we're going to use, d-dimensional vectors. Usually we use column vectors when we say u is usually a column vector. Here you see the column vector, and then these bars here are absolute value, and the other things, of course, you know already. So that's just a warm up, and please have a look to really prove this. So it's not enough to actually know it also, but we want to get familiar with the type of proofs that we need to do, because this type of argument will also help us for the proofs we do on the optimization algorithms. That's this. And how to interpret this? In this example, again, it's just to give you a better intuition, and it's very nice to actually tell you about the cosine between two vectors. That's what this inequality is doing. So because it's saying that the inner product is always smaller than product of norms. If you put this together, then you see that it's just saying that the cosine is between -1 and 1, and this can help you to do the proof of this inequality, and to also understand when is it actually an inequality and when is it an equality. So that's something to keep in mind here. So just as a motivation, so to say, for the type of math that we're going to use in this course. Okay. Now this I can do quickly. So I think you already know what is a convex set and what is a convex function. So convex set is very trivial, just for any 2 points xy. You have that their convex combination is also in the set. So that means for any convex combination, that means, so we pick a weight value between 0 and 1, and we ask if the convex combination is also in the set. If that's the case, then we can say this set is convex. It's, for example, the case here on the left, and so here is good. And what we see here, you have that it's not the case, and here you also have it's not the case, because this here you have that the boundary is sometimes included, but in this part here the boundary is not included. So you can find a point between 2 points in the set, and that between point is not included in C, therefore not a convex set. That's going to be important. And very basic observations you can make from here. Please also go over this in the notes again. You will see that, I mean, this you probably already know, that convex intersections of convex sets are also convex still. Unions of convex sets are not convex, actually, because so if you look at this, here you see that the intersection of two sets is fine, it's convex, but then the union of these two convex sets, that's unfortunately not a convex set anymore. So that's going to be also a useful property. And also one last thing I want to mention, should maybe get out of the way here, is that what is a projection onto any set. So here what we arc mean is a point which minimizes the function. So this is the projection. You might have several y's which achieve it, but the point here is that for this particular case, when we have a projection onto a convex set, so C is a set, if that's the case, then the projection is actually unique, which we're not going to prove here, but this fact here is very easy to prove and a good exercise for you. So that's about convex sets. I'll go quickly because you probably know this already. Same to say about the convex functions. That's equally simple. Any function has which satisfies this simple definition here, that for all x and y's in the domain. So the domain of f is the set of allowed points where your function is defined. So there we can talk about f. If for all these points you take a convex combination, and if you do that, and you get to a point here which is the convex combination. So here is f of the convex combination. Sorry, lambda x plus 1 minus lambda y. So if that point here is below the line which interpolates the two function values, if that's true for any pair x and y, then you're good. Then we call this a convex function. So here on this plot we have f on the vertical axis and x and y on the x-axis. Sorry, there it is. Okay, you know this, I think, and this is the basic definition of convexity. It also helps us to define what is actually a graph of a function, and so that you should also not forget. So the graph of the function is the black line here. So this is the graph of the function, and then everything which is above the f, that will be the epigraph, but that's something we will get to in a second. So far so good. I think you know this already. So why is this interesting? So there is a big literature and really often used results which are on convex optimization, and we're also going to spend a bit of time to discuss those in the course. So what is a convex optimization problem? It's quite simple. If the function is convex, which you optimize, that's one thing. And the other thing is that we also ask that the constraint set, so the set C we optimize here is also a convex set. That's then we say that we're doing a convex optimization problem. So the whole thing together is a convex optimization problem. The set should be called C, maybe that's a typo. Okay, why is this nice? It's quite useful because we understand that first of all we don't have local minimas here, which is super useful. That's something which is often a problem in like machine learning applications, in deep learning, where you have many potential local minima. For example, if your function looks like this, so we'll get to this in a second. So the good thing is that here you don't have that. So we have much better theory for problems of this form, and it's also going to help us to understand how the algorithms behave even on non-convex, because the progress that the optimization algorithms make kind of always comes from the convex world. That's why it's important for us to actually understand how they behave in the standard convex problems. So, okay, so can we do this provably? And that's a bit the overall theme of the course. So this is not yet the actual formal theorems. It's just to give you a flavor or an intuition of what we're going to prove in this course. What we want to show is that we run a standard algorithm which is iterative, step by step. The number of steps we do is t, small t usually, so for time. What we would like to have is something like this, that we would like that the progress we do, or the error we currently have, that's like what do I have now compared to the optimum. That's the error at the moment. We want that this error goes down with the time t. So for example, it should go down with 1 over t, proportional to 1 over t. That is the type of convergence theorems that we can prove for all kinds of algorithms. We will start with gradient descent, and we will look at the important case of stochastic gradient methods. And the rates will always be slightly different depending on the algorithm and depending on the goodness of f, like how complex, how nice is my objective function f. And the nice thing is, in the convex world, we can prove that it will go to 0, right? It will go to a perfect optimizer. So x star is an optimum, there might be several. So it will go to the perfect optimum, and as we said before, there will only be the optimum is unique. I mean, the optimal value we can achieve is unique. There might be several x star which achieve the value, but the value is unique, and we can reach the value, which means we can get 0 error in this convergence. So that's the nice thing in the convex world. And the same proof will also help us to say what happens in the non-convex world, where we can say that at least we make progress towards the convex landscape, which is local to us, maybe not the global landscape. So, okay, so this is the type of results which you will discuss in the course. If you wanna get a more overview how these things look like, as you can see on the left, you have different classes of functions. So if the function has this and that property, for example, it's smooth or it's not smooth, depending on that you get different rates. What is the error after t steps? And you can also discuss how expensive is your algorithm for one step. So that's also a consideration. Just the fact that we need very few steps doesn't make it the best algorithm, because we have to consider the cost per step. So actually here in this column you see how many steps we need to reach an accuracy of epsilon, and so that's kind of equivalent of saying that the error decreases exponentially in t. That means to reach accuracy epsilon we need logarithm of 1 over epsilon many steps. So this is the type of results we talk about in this course, and gives you a bit of a preview. If you want, there is a nice overview survey paper by Sebastian Bubeck I can recommend if you want to look up all these precise rates, and some of them we will discuss in the course. We will focus on the most important ones for machine learning applications. So, okay, small additional bits of terminology. This is not going to take long. So as we already said, what the graph of a function is, we discussed this. It's just all the pairs of input data points and the function value. So the graph is actually a part of not the d-dimensional space, but the d+1 dimensional space, right? Because you have d variables, ux, but then you also take the function value. So therefore you talk about a point which is now in d+1 dimensions, So that's your graph. Everything which is above that, so those alphas which are above the graph, this is called the epigraph. So that's what I briefly mentioned before. So that's what you have here, the epigraph of a function, and on the left you have it for a non-convex function, on the right you have it for a convex function. So it seems interesting that we talk about functions being convex or not, and we can talk about epigraphs being convex or not. I mean, the epigraph is a set. So what is this relationship? Is there actually a relationship that functions are convex? Is this the same thing as a set is convex? So that would be nice, right? It could be surprising if these two concepts are related, because a priori it's not. Well, why would functions behave like sets? But actually they do, and this is a theorem here, or an observation, that a function is actually convex if and only if its epigraph is a convex set. So that goes both ways, and that's a very nice thing, and again helps us to get into the right type of arguments and thinking we make here. So let's prove this. It's very important that we get familiar with proof strategies. And of course, this one will be simple. It's again kind of a warm-up, but I really suggest you to do this one yourself to be sure how this works. So what we want to prove is that the function. So again, yeah, here you have your x-axis, right? So and then here is your f of x, and then the sets are here in d+1 dimensions, and we want to prove this equivalence. So how do you do this? So we have to prove two directions. We have to prove from left to right and from right to left. So that's our goal. Let's do this. So I want to prove the first direction from left to right first. So I want to show that, what is it? Yes, assume the function f is convex. Can I prove that the epigraph is a convex set? Can we do this? So that's what we want to do. So I want to prove that this thing is a convex set. So how do I do it? I of course need to show that for any pair of x and y's, or a pair of 2 points, I need to show that their line segment is also included in the set. And the set here is the epigraph, and here you have a recap what the epigraph is. So these 2 points are in the epigraph, so they come in this form to us. They come in the form of an x and a value alpha. And here we have a y and a value beta. And they are in the epigraph of f. What that means is that it just means that alpha is above f and beta is above f at y. So that's what it means. This is what we have, but now we need to show what happens with their combination, what their convex combination is. So that's alpha. That's my first point. I take it with a lambda weight, and I combine it with 1 minus lambda times the other point. That's y and beta. Okay, so that's my point in the middle. If you want, this can be green. So what about this point? Is this part of the epigraph or not? How do we find out? So what can we use to prove that? So it's very simple. You will just take it separate. So this point, of course, is I just can combine the first two arguments, and then I can combine the 1 minus lambda alpha and beta. Nothing has happened, but now we can see why would I say that this guy is above that point? Because if I could show that this value is above the function value here, then I would be done, because then I would have to show that this point here is in the epigraph. And what can I use? The only thing I can use is f being convex. So remember, we go from left to right, so we assume f is convex. We want to show that the set is epigraph is convex. That's what we want to show. So we want to show that this point is part of the epigraph. What we can use is convexity of f. So f of sorry. So this we know, right? That so now I will just apply convexity at this combination of x and y. So this is nothing special, just convexity. But now I also use this for my particular point, so I know that I can write this for alpha and beta. And now I'm done, because now the point I have here, that happens to be exactly the value here. And what I have shown is that the guy on the left has a function value which is smaller than that. Therefore, my entire data point here is part of the epigraph, and I'm done. So it's an element of the epigraph. So I finish my proof. Okay, that's again very simple toy proof, but helps us to get into the mood and to do similar proofs. So for the next arguments, this will also be useful. And the other direction you can imagine is very similar. So I will now assume that epigraph is convex as a set, and I have to prove that this implies that the function is a convex function. So EPF is convex. And that is also very simple to use. So I can now take any 2 points in that set, and I can use that their line segment will also be in the set. So that's my tool. And how can I use that to show that my f is convex? So what points should we take? I pick 2 points, and then I will build a line segment between them. So of course it makes sense to take x and y, whatever they are. I take these arbitrary. But what function value should I take? I can take anything in the epigraph. So just want a point with x which is in the epigraph. So what might be a good idea here is to take x together with its function value f of x. That's a particular point in the epigraph. I could take any value here which is higher, right? That'd be good enough. So anything is fine here, but I choose to look at this very particular point f of x and f of y. These are my 2 points in the epigraph. What does that mean? It means that also their convex combination is in the set. So let's do it. What's the convex combination of this? So here's the convex combination, is in the epigraph. I know this. Why? Because I'm using that the epigraph is a convex set. And why is that useful for me? Because this is equivalent to the claim of convexity. So So again, this gives the climb. So here the key was, we just had to be smart about which point we were choosing. So for this particular x and y, this worked nicely. So to show that the function values are related, and how are they related? If you formulate that this thing is in the epigraph, then you exactly get the definition of convexity. Great, so that's a good experiment to do, or good kind of proof to do. What else? So this is, you can remember this, so this will now have in our toolbox for the future. We can always use this fact if needed. And what else do we have? Convex functions. You have seen many of them, right? It's not that it's an artificial concept, but it's actually appearing a lot also in nature. There's a lot of linear functions going on, where you just have a high-dimensional weight vector, for example, vector A in d dimension, defining some kind of weights, and now you have a linear function. If affine functions is the same thing, but shifted by another constant. We have some kind of functions which you're also very familiar with, like exponential function. And so that is a function now here, it's a one-dimensional function, right? So from a one-dimensional x. And here we were talking about d-dimensional functions, multivariate functions. And also the fourth example I want to mention are norms. Any norm is actually a convex function. That's another claim which is maybe worth thinking about a minute or a few seconds. And that's a great little exercise again. So basically it will come directly from the triangular inequality to show that any norm is convex. So here is the proof what it means to be convex. It's just a definition. You use triangle inequality. So here you have a sum of two vectors. So you say that this is smaller than the sum of the norms. So that's the first step. And then, so that's what we have used here. And then in the second step, we used that the lambdas can be taken out as a norm. That means that the norm is homogeneous, that the scalar can be taken out. So we have proven that any norm is convex, which is very convenient. And this is also going to appear a lot, I think, in the future. Finally, this tool we should not forget, which is very famous, which is very related as well to convexity. And what that means is that if you have a convex function, you can again combine several points and ask what is the function value at the combination of these points. How is that related to the combination of function values? It's very similar. You have this actually. The basic definition of convexity just has 2 points, like x and y, and we asked function at the combination of x and y, how is that related to combination of the functions? It's the same thing here, except that the only difference here is that we have taken more than 2 points. We can take 1 to m points, many of them, and we can take convex combinations of these m points with weights which sum up to 1. Remember, same was the case for 2 points. So if the weights sum up to 1, then we have this inequality, which is called Jensen's inequality, and this is going to be very useful as well to deal with. Maybe we want to talk about the f value, but we have combination of points. So then we can use this inequality, which is at the core of many of the convergence proofs in gradient methods. And the case m equal 1 we mentioned already, so that's really, as we said, it becomes convexity. And what's also we shouldn't forget here is that this is a very good exercise for you to prove it. So this is actually one of the first exercises of this sheet of this week, this exercise sheet. Please have a look. Take a shot at this proof that you have the necessary tools to prove this inequality for any bunch of points with weight summing up to 1. Can you prove this? And we will show you the solutions on Friday. So, but please have a look during the week already, so you can benefit from the Friday class. Okay, another property we have from convex functions is that they are actually continuous, and that's also something which sounds easy, and it is actually quite easy, but it's something which is important to be precise about. We should not just take it for granted, but actually prove that. And that will be also quite easy if you know the definition of continuity. So if you have kind of two points and you get arbitrary close, then the function value should also get arbitrary close. If not, something is wrong, right? This step function here is not smooth, and well, this function here is kind of smooth or continuous. I mean, continuous smoothness is a way to quantify this. So the definition of continuity is actually going to follow from having convexity. So convexity is a stronger property than continuity. That's what this is about. Again, small exercise for you and great for training. And then we have to talk a bit more about what is actually different, what is the derivative, what are gradients, and so on. So here you see this crazy object for the first time in this course, which you probably have seen before, which is the gradient. And why it's useful to describe functions is because the gradient is like the best first order approximation to the function. It gives the best such approximation because it defines the tangent plane to your function at your current point of interest. So you're located at x, and you ask what is the linear approximation to my function at this point x, and the answer is it's the first order Taylor expansion, which is the just the current value, which is fixed, and then it varies here as a linear function defined by the first derivative, which is called the gradient. So gradient is here's the definition. It's just collecting the change rates of your function depending on the first variable, depending on the second variable, depending on the last variable. How fast is my f changing? That's what it is. And why are we mentioning it here together with convexity? So here is a kind of a very strong result which we're going to use quite a lot, showing that if you have gradients available, then you can say even more easily, more clearly what it means to be convex. So if you have gradients, it just means that your function is convex if and only if the function always above its gradient. So if the function always lies above its gradient, then you have a convex function. So which was here it was not the case, right? Here we had our function going up and down here. But if you imagine a different function here, so for example this one, that also has a tangent wherever you wanna look at, and in this case you see that your green function is always above its tangent, therefore the function f is convex. That is what this lemma here claims. So that's very important. But you can only have this if and only if you can only have this equivalence for differentiable functions, and we have to assume for a technical reason that this is kind of an unconstrained problem. We want that the optimum does not happen at the border of the domain. That's why we assume that the domain is open. So the two small assumptions here being the domain is open or infinite, like the whole space, the whole Euclidean space is an open set and it's also a closed set. It's both at the same time. So that is a small technical assumption. But what the big assumption is that f is differentiable. So if my function is differentiable, then I can say it's convex if and only if we have this condition here for all x and y's. So you go any x, you do your linear approximation, and then you say at any y, so here is your y, any x, any y, the y must lie above the linearization. So here it's actually not the case. So here you can say this condition is violated, right? Because this point y does not lie above the linearization, but it's below. So it violates convexity. So this is a useful lemma and also not hard to prove. So, and here is, yeah, exactly the same thing I said before, but now actually for a convex example. So, okay, nothing so surprising here. I just want to say that it's not enough to limit ourselves to discussions of only differentiable functions. So this is actually a big assumption, and also in machine learning it's important to sometimes discuss non-differentiable functions. Non-differential functions are real. They happen all the time. So in machine learning you also have this, for example, this ReLU activation functions. So rectified linear unit or the hinge loss. So which are very simple functions, which are mostly linear. They're linear in all pieces. So here 2 pieces, they're linear, but there's like one point between the pieces where they're not differentiable. They are continuous but not differentiable. So make sure you're familiar with these basic notions from analysis, calculus. So we need to know what differentiable means, we need to know what continuous means, and the convexity I also already showed you. So just to say it, yeah, many real-world examples are not always differentiable. The situation is not so bad, right? Because it's kind of differentiable everywhere except at one point. That's what happens in these 2 examples here, or even the third example, which is the so-called ice cream cone, which means the norm of the Euclidean norm gives its function as a function, gives this ice cream cone as its graph. Okay, they are not differentiable at all the points, but they're differentiable at most of the points. So we will also discuss algorithms for this case. It doesn't mean that we can't solve it, and there's actually still convex functions in this case, but if you're convex, it does not necessarily mean that you're also differentiable. Okay, we talk about convexity in this chapter. So before we finish it, I want to give you this one more characterization of convexity. So characterization means it's an equivalence, right? It describes precisely when the function is convex or not. So here we look at the second derivatives and we try to use that to decide if our function is convex. What is the second derivative of a multivariate function? It's here. You just take the first derivative, which is the gradient, and then you take the derivative again. So what it is a big matrix, which is D by D matrix, and that's called the Hessian matrix actually. So the Hessian, you might have heard that before. It's way too big if you have like millions parameters. So D is a million, then this would be too big even to store. Yet again, to compute it is also associated with a lot of cost. But even storage is a problem here. But that's not the point here. The point is to theoretically describe how these objects relates to convexity. And there is a relation, so if you have this second derivative, that's like before, we assume that derivatives are available. So let's assume we have a second derivative of our f, and same assumption as before. So then what can we do? We can look at it and we can try to decide if he helps us to say if f is convex. And yes, it does help us. F actually is convex if and only if this object is a positive semi-definite matrix. So this matrix has only non-negative eigenvalues. That's what we are talking about here. That means that so this second derivative describes the curvature of the f function. So if it tries to approximate it in the second order, so it's curved either like a parabola upward or it's curved downwards. Or it could be a saddle point, and it has both negative directions and positive directions of curvature. Here what we're saying is that if they're only positive directions of curvature, so these are the if they're only positive eigenvectors, if all the eigenvalues of this matrix are positive, non-negative, then we have that f is a convex function. So that is useful if you have this matrix available, and actually this is also very important for second order algorithms. There's some very fast algorithms, for example Newton's methods, which use this matrix here to perform good optimization steps, and then we will also see how this relates to convexity. Okay, but for now, remember we have seen two characterizations of convexity, or three of them: the initial definition, then we have seen the characterization if you have gradients only, to be above the gradient. And here is the other characterization we have if you have the Hessian. Then you can say it's convex if and only if the Hessian is PSD, positive semi-definite. So yeah, check this on a small example. That it's helpful to also get familiar to compute these second derivatives. That might be useful. That's important that you also try this in code, that you're able to take the derivative, for example, in PyTorch or so, and then you will also sometimes be able to take the second derivative and look at it at certain points. So here for a quadratic function, the Hessian actually depends not on x anymore, so the gradient depends on x, but the Hessian turns out to be a constant matrix independent of x, and that matrix happens to be a positive one in this case, so it's a convex function. Then another tool set which is useful for us is to say that convex functions can be combined, and you can maintain the property. Sometimes one way to do that is simply to build linear combinations of these convex functions. Then it's easy to see that the linear combination, which is here, is again a convex function when the original ones were so. So that's easy, just adding the functions with some weights, right? So that changes nothing. It's very easy, small exercise. Another one is if you take the composition of convex functions. So you have one convex function and you plug it into another one, you would think that the composition f applied after g is also convex. Turns out that's not true. It's not true for general f and g. Composition is not always maintaining convexity. However, it does preserve convexity in some cases when the function g, which is the one you apply first, is a bit simpler. Then you can actually preserve it. So if the inner function g is a linear function or affine function, then this is true. So if the inner function is linear and the outer function f is a convex function, then their composition is still a convex function. Can also be useful to decide in some cases. All right, I think now we have most of the tools. What this is kind of a very nice result to actually understand provably that the convex problems can be solved, that they actually do have a global minimum which we can find, and that they do not have any local minima. So what we show here is any local minimum you find is a global one. And that's very nice, and that's something we only have for convex functions. That's the summary of this slide, but before getting there, let's do it step by step. So what do we even mean by a local minimum? So it's very important to be precise here. So what we mean by local minimum is that it's a point x together where there exists a small radius epsilon, that around this small radius the function here, so you can look at the small radius from left to right here. So you see within this radius the point x is actually optimal, right? Everybody in the neighborhood of x has a worse function value than x. That's what it means to be a local optimum. So for all y's which are close to x, not too far away, they have a worse function value. That is a local optimum. Now we have such a local minimum, and we ask what does it have to do with the global minimum of the function? And what we're now going to say is this super nice result, or theorem here. It's just called a lemma because it's so easy to prove, but it's quite beautiful that every local minimum here of a convex function happens to be a global minimum. So if you have this condition locally, then you also have it globally for all y's in the definition, in the space where f is defined. So that's every y in the domain of f. Why is this the case? So that's important to prove, and we prove this by contradiction. So we want to prove that this holds globally, right? The way we prove this is that let's assume it does not, and then let's see that some crazy stuff happens and that we arrive at the contradiction. Therefore, we will say our initial assumption was wrong, and actually this does hold everywhere. Let's assume it does not hold. So that means there exists a y where the value is better than this x star. So remember, x star here is only a local optimum. So x star is one local optimum. We assume there is a better point. Now so here is your x star in the picture, and now you take the line segment from this x star. And you take the line segment from that x star to your better point, which we call the y. Now, because that line segment is connecting these 2 points, the x star to a better one, we can see that this will actually mean that the line, if you go close to x star, then you will still be better than that, right? So because y is strictly better, so strictly better than x star. Therefore, if you are on this line segment, getting closer to x star, here's your y. So if you get quite close here, you get into this neighborhood of epsilon radius. You see that you will get very close to x, but you will still be strictly better than x star. And that is impossible. That will contradict the property that x star is a local minimum. So we have arrived at contradiction. Therefore, we have it's not the case. Therefore, x star is actually a global minimum, and that's the whole proof. So this is quite nice. And what we have done here is just using convexity, right? So when we said everybody on the line segment is also better than the two endpoints, or the combination of them, that was exactly where we use convexity of f. So you cannot have this situation here in this plot here. So because we went on the line segment, right? We went from this x to the y, and we said that it's not possible that you go up and down here. That's the proof that we have done. Okay, we proved this, and it's very useful. And so we have now found a proof how to find global optimum. We can just say take a local one and you're done in the convex world. There is another way to do it. So if you have an additional property that you are also having derivatives, then you can just say that when do we have a global optimum? It's very simple in that case. We can just look at a point where the gradient is 0. And that will be, if we find a point like that, then it's proven that this is also global optimum. So that is also very nice, and also almost trivial to prove. And yeah, remember the definition of this critical point. This is going to be critical for deep learning. So in deep learning we have in a non-convex situation where we cannot always talk about global optimum, but we will always talk about critical points. Can we find a point where gradient is 0? And what this result here says is that critical points in the convex world are always global optima. Why is that? So we need to use this fact that we are at a flat point. So I mean we are at x and the gradient is flat, 0. So function doesn't change. So what does that mean? How can we use that to talk about optimality? So we want to use convexity of f. That's a crucial assumption. So we have seen like 3 variants of convexity. So here we will use the most basic one, which is from, if you have gradients, you have the first order characterization of convexity. That's what we're going to use. What it says is that any xy, f of y will always be above f of x plus the linearization. Let me write this. So here's gradient of f of x minus y minus x. And there is a transpose here. So the point here is that the gradient of x is 0. So my linearization here is 0. So this is for any point y in the domain. So we are done. We have shown, any y in the domain. So we have shown that any point y has a better function value than f of x. Therefore we have shown that x is a global optimum. And how have we done that? By using first order characterization of convexity, which we've just seen 10 minutes ago. Okay, that's not a very nice result. And that almost brings us to the end of this main results on convexity. So these are really crucial results on the global optimality, right? We have seen 2 of them already now. So before we finish, we just have this slight extension of convexity to also say there is a notion of strict convexity. And this is really easy. So what we have seen before so this was a convex when this inequality was true for was equal or large. The right side is equal or larger than the left side. That was convexity. And now we have strict convexity if this inequality is true strictly for any convex combination. That does not work actually for any convex combination. You need to assume that lambda is between 0 and 1 strictly. So that's another small technical difference. But other than that, exactly the same thing. But now you just have that you must be strictly above. then you have the function can be called strictly convex. So this is the case on the right, yes. This is not the case on the left. Why not? Because you have 2 points here where the function is directly on the linearization. It's not above the line segment. Okay, why is this interesting? So this is a bit less practical, I would say. In practice, we often have convex functions which are not always strictly, but many of them are. For example, the Euclidean norm squared is a strictly convex function, which is something we're going to use maybe later. So why is strict convexity useful? If you're strictly convex, here's a little lemma showing you that then there is exactly one global optimum at most. So there cannot be several different global optimas. There will be at most one. There can be none, which is a good exercise for you to think about. For example, if you have the e to the x function, which has no, e to the x is here, has no no strict, the minimum is not necessarily attained, right? There's many functions which are convex, but the minimum is not, sometimes you have not one particular minimum, so it might be convex, it might be strictly convex. Nevertheless, this lemma is true. F will have at the most one global minimum. All right, and the very last thing today will be about constraint problems, which is also something worth mentioning, because sometimes there are constraints in life or also in optimization that we have to respect certain restrictions. Here the restrictions are on our variable x. So x is not just any point, but when we optimize our f, we need to restrict ourselves to a particular set, and that's x here. So this is called the constraint set. Remember, what we've seen so far was kind of unconstrained optimization. We just had that x was the whole space R to the d. Then that's fine. That's a special case of what we have here. But what we're saying here is that there can be subsets. Sometimes people are interested in a subset of the domain. They want to optimize only over x, which are, for example, positive. They want to only optimize over x with certain properties, like summing up to 1. Or there's many applications where you will have a constraint you need to respect on your optimization variable. So that's x, my constraint set. All right, and now what's not so clear is if we have constrained optimization, can we still talk about optimality in this way? So. Is there a first order optimality condition in this case? It's not obvious, right? Because remember when we stated the first order optimality, we assumed that the domain is an open set, and then this was fine. But here we're now actually becoming more general. So here we have an arbitrary set f, and we talk about a minimizer of the function over x. So this is the set minimize, but only minimize over the set x. So what's the optimality condition? There is one, and it's written here. It's again, so before when we are unconstrained, we could just say gradient is 0. But now actually there is a more interesting condition now to say that the point x star is an optimal point for the constrained optimization problem. So this also needs to talk about the relative position of x star compared to the set. And the way it does that is to just say that, so I'm currently at x star, and no matter where I walk, it's going to go uphill. It's going to make me worse in function value. So you can, I don't know if I'm able to draw this, but you can imagine you're stuck, or you're located here in x star, and what this condition is saying that anywhere you go, if you go inside the set, if you go towards there, it goes upwards, And maybe if you would go in directions outside the set, then it could still go downwards in terms of f, right? So here that still means, in this case, the x star is still optimal for the constraint problem, because I cannot stay in the constraint and improve my value. If I improve my value, which is green, then I leave the set. So, but if I stay inside the set, which means I go in a red direction, then my value gets worse, so therefore my value is optimal compared to relative to the constraint optimization problem. So this is what that means, the vector from x star to x. So it means that I go from the optimum to somewhere towards inside the set, because x is inside the set, and then the gradient is relative to that direction, so that if you project them onto each other, they're positive, so it goes uphill. That's what it means to have this optimality condition for constrained optimization. And this one as well is maybe worth thinking a bit more if we can prove this, that this is actually a if and only if condition. With that, I think I will leave you for this week. So here is the visualization of this, and have a look at the exercises, and this one will actually make it optional for this one if you're interested. And next week we're gonna actually use the tools we have here to prove the convergence rate of gradient descent methods. So, and with that, see you next week.